there?
No.
Okay. Okay.
You know that you didn't get it.
Go ahead and get started. All right, so last time we did some carbonyl chemistry. We talked about how the stretching frequencies for COs are a really good handle for understanding the type of carbon monoxide linkage you have, whether it's bridging or whatever. We looked at a few different examples and how that frequency moves around. There are characteristic ranges for each type, and that's really useful. In general, of course, how electron-rich the metal is will dictate that frequency for a given coordination mode. We also talked about NO. NO is this sort of complicated beast where you've got one more valence electron than carbon monoxide, so it can be an X-type ligand. But if it goes linear, and it takes the same geometry as the CO, that electron transfers to the NO being a 3-electron donor. And there are multiple resonance structures you can write where you have metal nitrogen triple bond, nitrogen oxygen single bond, or the opposite extreme. And you need to be able to do all those resonance structures and get the formal charges right and to understand the oxidation state change. Everybody struggles with this until you go through it a few times, and then it's still not that intuitive. I'm always looking at that thing, like crunching the numbers. I stopped trying to analyze the structure because now I just know. The drawings are confusing. You're going to do that on the final exam. Okay, so make sure you can do that. Do it from scratch. So we're going to switch gears a little bit before we continue talking about ligand types and coordination chemistry. And we're going to talk about how you can use group theory to determine the number of vibrational modes. You've got CO ligands. You can get multiple different vibrations for them. And so if you look at the infrared spectrum, you can look not only at the frequency, but at the number of peaks and make an assignment of the type of molecule you got. All right, so let's take a look at that. So in a molecule, any given molecule, you get a number of vibrational modes that are possible. That's defined by the number of atoms. It's 3n minus 6, where n is the number of atoms. Unless the molecule is linear. Yeah, minus 5 in that case. Okay, so now that's a lot of vibrational modes, right? Most molecules have 10 atoms at least. And so we end up with quite a few vibrational modes possible. All right, so then the question becomes, which of those modes is sort of relevant for an infrared approach? And let's take, for example, an octahedral compound like chromium hexacarbonyl. Yeah. 2 times 6 is 12, 13 atoms here, so 3 times 13 minus 6 is 33 vibrational modes. how many of those are active in an infrared absorption experiment? And so we talked about the probability of a transition or whether a transition is allowed. We talked about electronic spectroscopy. The same kinds of rules apply here. The primary thing being whether or not the transition has a dipole moment that develops when the atoms move. And so which of these motions, these vibrational modes, will have a transition dipole moment? And it turns out you can determine that using group theory. Okay. So what we're going to want to do here to figure that out is to analyze these motions where the motions are the basis set. Normally it would be the orbitals are the basis set. This time it's the motions that are the basis set. So you can think about this thing as having some kind of a motion, a stretch along this bond, right? The oxygen moving that way. And every one of those has that type of motion. And then you can make linear combinations of those to obtain the normal modes of this complex. Look at the irreducible representations of those motions. Right, you got all these orbitals in a molecule, you mix them together, pull out the MOs, you want to find the irreducible representations of the wave functions that have the same symmetry. We're going to do the same thing using those motions. Right, so we're after gamma 6 nu CO. And it turns out it's the same thing as the sigma basis system. Right, so it's basically the same thing as 6 ligand sigma. That's A1G plus EG plus T1G. Well, what are these things? What's A1G? Yeah. What does that mean? What is it in the orbital world? It's totally symmetric. What does that mean in vibrational motion world?
I mean, like all the ligands moving away or towards the metal?
Yeah. It's kind of the sign of their motion. It's all the same direction at the same time. Okay. So this guy here is all moved together at the same time. Phase. Okay. These guys, what's that? Move and breathe.
Right. The molecule symbol suggests that there's two, thinking of like the degeneracy piece. The E means that there's two sorts of like motions going on at one time.
That's true. This one's doubly degenerate. What do the motions look like, though?
Moving towards and away. Maybe the axial one moving towards it.
How did you know that?
Just because there has to be two types of motion.
There you go. I like to think in orbital terms because I know what the orbitals are. I'm used to that, right? What's the EG and what are the d orbitals? It's c squared and x squared minus y squared. Okay. So you can look at the lobes, say, of x squared minus y squared, and where it's shaded, it would be plus, and where it's not shaded, it would be minus. the plus and the minus refer to the direction of motion. If it's plus everywhere, they're all moving out. If it's negative everywhere, they're all moving in. If it's plus along this axis and negative along this axis, that means that they're just they're in phase across the molecule, but out of phase adjacent to each other. Right? That's what the signage is on the x squared minus y squared. A dz squared orbital, you've got lobes here and here. These two guys are going to be in phase. These two are going to be out of phase with these four. That's where the donut is. These four will be in phase with each other, but they're going to be out of phase with respect to these two. Okay? So the plus and the minus signs on the orbitals are tell you what the motion is. How about this one? What was T1U? No.
100 times Q1, that's why Z.
Okay, this is Px, Py, Z. What does that look like? That's the same direction for all. Let's A1G. Let's do an EG. We decided this is going to be like dz squared, right? That's the normal mode. There's also this other one. Like e squared. This is like x squared minus y squared. What about this? Don't you like? I'm putting you on the spot there.
I'm looking at the x squared minus y squared, the second one, and they're opposite.
So let's draw the d orbital just for.
Oh, okay.
Huh? Okay, let's do T1U. What did we say it was? What's it like?
One stretches one along the opposite one on the axis along.
That would be like PZ, right? This is the plus direction, this is the minus direction. Why is it minus if they're pointing the same way? Because it's with respect to the metal being in the center. Okay. This is where they're all plus.
So you're saying that one going away from the metal is plus.
Yeah.
Since that's going towards the metal,
It's when.
It's making a minus. Now,
In other words, they're out of phase.
they're out of phase.
Yeah.
So does that have to do with the dipole? Like moment on this molecule?
This molecule does not have a dipole moment. But does that motion have a dipole moment?
Transition.
We're looking for transition dipole moments, right? Why do we need a transition dipole moment? What does that do for us? It makes it interact with a photon, because a photon is an oscillating electric field. And an oscillating electric field has to push charge around. And these motions move charge around. But it has to couple with the field. So there has to be a net charge motion in one direction for that excitation to happen. Which of these has a net dipole moment? Which motion causes a dipole moment, induces one?
T1U.
What's the charge on this oxygen here? I mean, relatively speaking, you know, like there's this diagram or this resonance structure depiction we made where you push electrons out onto the carbon. You get triple bond character with that carbon, and the oxygen develops a negative charge when that happens. Okay? That's kind of what's going on here. When you stretch this bond right here, this oxygen is moving away, you're kind of breaking that triple bond and making a single bond. Okay? So you're pushing a negative charge out this way. And here you're pushing a negative charge in this way. This develops a dipole moment. This motion couples with an electric field.
In the first EG, if we're modeling it off of a DZ squared,
Yes.
does that mean that the equatorial magnitude is smaller than the axial ones? Like would it?
Probably, yeah.
So the arrows in the axial direction could be like larger.
Yes.
And that's how it would induce the dipole.
I don't see a dipole moment here.
Yeah. Okay.
Remember that, like, so would you say an s orbital is a dipole? Would you say it's a quadrupole? Would you say it's a unipole? Unipole. How about a p orbital? It's a dipolar arrangement. How about a d orbital? It's a quadrupolar arrangement. How about an f orbital? That's a hexapole. That's a hexapole. Okay. So maybe it's tripole. No, it's hexapole. Yeah. So maybe you've never heard of a hexapole. So these types of motions here develop dipoles. They undergo absorption of photons. They will absorb a photon at the energy of this vibrational excitation. That's what's called linear spectroscopy. There's another thing called second order spectroscopy, and that involves quadrupolar transitions. What's a quadrupolar transition? The transition quadrupolar moment. We have such a thing here. An s orbital is a unipole, and a p orbital is a dipole, and a d orbital is a quadrupole. These things have quadrupolar moments. Does anybody know the name of the spectroscopy that causes absorption of a quadrupolar moment? What's the second order spectroscopy? Raman. These are Raman active modes. Raman is a second order spectroscopy. It involves a quadrupolar transition moment. These are the kinds of vibrational motions that are active in Raman. Okay. So, infrared selection. transition dipole. Which vibrational motions have a transition dipole moment? You look at the character table and you see, is this X, Y, or Z? Is it absorption? That's infrared absorption and selection roll. Let's do Raman. And with blue folder. Bipolar moments. Motions that transform like the orbitals. Linear absorption spectroscopy is a dipolar transition that couples nicely to an electric field. Quadrupolar motions, second order spectroscopy, usually involve two photons. All right, so these rules are great when you want to distinguish structures from each other. So we're going to see how you do that here. With this example, chromium CO4 E3. How many electrons? Eight, 4, and 6. 8. Octahedral D6, good chance that it's going to be 18 electrons. Octahedral D6 metal center is usually 18 electrons. Chromium, what's the oxidation state? Any X-type ligands? Any charges on the complex? No. That's chromium 0. 6. All right, so there's two different geometries. There's the trans. This. So, who's going to have more vibrational modes that are active in a Raman experiment? We're going to do group theory to figure it out, but I want you to do it without group theory for a second. Any guesses? I want a snap judgment. How about trans? How about cis? Why cis?
Less symmetric.
Less symmetric. It already has a dipole moment. Any motion is going to kind of strengthen that or weaken it, or basically any motion is going to be dipolar when the molecule has a dipole. Not necessarily, but so if the molecule itself has a dipole moment, it's going to have more. All right, so let's do, so this trans point group of this thing is 4. Anybody see a sigma H? There's a sigma H there, so that's D4H. And what about this one? Is it point? Points, doesn't it? It's got a dipole moment. It's a dipole moment's point. B. So. For new 0. Remember, we've got one motion on each carbon dioxide. We're going to ask if they move. What's the character under E? We got 4 motions, they're doing nothing, and then we're moving. E4. C4, all are moving. We get to 0. The C2 prime, where you have an axis going through one of the COs. 2 of them don't move, but otherwise everybody is getting 0s until we get over to sigma H. There's 4 motions in the plane, so we're good. Sigma B, 2 per plane. So, and then you break that thing down just like you're used to. Or new CO. Anybody want to guess what those might be? A1G plus B1G plus. Any of those going to be infrared active?
Just like looking at the Ungerard kind of implies that you're going to develop those dipoles.
Yeah, there you go. The U implies that it is anti-symmetric with respect to inversion. Right? And which kinds of orbitals are like that?
Spectrum inversion P orbital.
That's a P orbital. That's what we're looking for. Those are dipolar motions. So if you look at the character table, PZ is A2U. EU is PX and PY. So this guy is infrared active. Okay. Notice here's our Z direction. No COs along there. Okay. That's why it doesn't appear. But X and Y, So you get one doubly degenerate band. For motions again, where's our C2? How many of them moved with the C2? All of them move. Sigma V, XZ, and YZ. 2 each. So how many infrared active modes do we have here? Well, this is PY-like, so that's definitely active. This is PX-like, so that's definitely inactive. These two are both PZ-like, so they are both active. There's two different motions here. They may not be at the same energy, or they might be. In fact, all four of them could turn out to be the same energy. There are 4 distinct modes, and you may see 4 P's. Okay? Even though 2 of them have the same symmetry. All right, so 4 modes. Okay, so when I look at a molecule and I'm asking myself, how many modes do I get? I just look for PX and PY and PZ and count. Are PX and PY and PZ distinguishable from each other or not? How many COs are there? That's how you figure it out. Right? If the molecule has a dipole moment, any of the motions really are going to be active. Okay? All right, so say goodbye to group theory. You guys did so much of that stuff this year, and look at you, you're blasting through these problems now. You know exactly what you're doing. That's pretty awesome. All right, so let's talk some reactivity. I want to just give you a sense of how COs tend to react. So a lot of CO chemistry. Carbon monoxide is one of the most important industrial chemicals. You can make anything out of CO. Things that have carbon in them can be made out of CO. You can make gasoline out of CO. You can make hydrogen out of CO and water. You can make ethylene glycol, you can do blah, 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 blah. It is basically like the most potent building block. It's made in gigantic quantities. There are facilities that could fill a football stadium with carbon monoxide in a matter of minutes. Out there, they're the size of small towns. Huge amounts of CO made every year. So lots of carbon dioxide material. Loss of CO. Let me just say one more thing about that. I don't know if we're going to talk about this reaction or not. There's a reaction or a process called the Fischer-Tropsch process. Fischer-Tropsch is a really important reaction, and it takes carbon monoxide and hydrogen, and you can make all kinds of chemicals out of it. But Fischer-Tropsch usually refers to the synthesis of diesel. Okay? It's really hard to beat the energy density of the chemical. Batteries are pretty good, but not as good. You know, flammable chunks of lithium, not as good as oxygen and hydrocarbons. So planes, it's going to be really hard to replace diesel fuel with a battery for the sake of flying a plane across the ocean. So you can make diesel fuel from carbon dioxide. You can take carbon dioxide and hydrogenate it and make carbon monoxide. Take carbon monoxide and hydrogen and make diesel fuel out of it. So I think it's, I mean, there are facilities all over the world where diesel fuel is manufactured from carbon monoxide, either made from natural gas or made from coal. Really important industrial process that's going to gain in speed. So not all diesel is bad. All right, so let's talk carbon monoxide. Classic reaction. Seems boring, but loss of carbon monoxide from the middle center. That's an important reaction. One of the ways you make that happen is with light. Shine light on your compound, and the CO pops off. You excite a metal to ligand charge transfer band, and then the electron falls down into the sigma star, and then the bond gets really weak and the ligand falls off. So loss of carbon monoxide can produce this iron tetracarbonyl. We've got 8 electrons for iron, ruthenium, and osmium. We've got 8 electrons here. This is a 16 electron compound, and it is very reactive. It will react with another iron pentacarbonyl because it's maybe swimming in iron pentacarbonyl. This is a liquid. Kind of cool, it's a liquid. So you shine a light on it, some CO pops off, you generate some of this, and it grabs a neighbor. And you end up with this iron 2 CO9 dimer. This thing is kind of cool. A little bit like that. A couple of bridging carbonyls, some terminal carbonyls. Let's count some electrons here. Symmetric compounds, so we could do the all electron method. We've got 8, and 8 is 16. How many COs do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. 2 each is 18. That's a total of 34. That'd be 17 electrons each, wouldn't it? So what's missing from my drawing here? 17 electrons. Odd electron iron is just going to pair up. Level bond. So now we've got 2 irons equals 16. We've got 9 COs equals 18. We've got this iron bond. $18 electrons each. keep zapping this thing. Eventually we get to iron 3. Well, if you don't have light, this reaction still happens. You still lose carbon monoxide at room temperature, but it takes a really long time. T1/2, what's a T1/2? T1/2 for this reaction is 4 years. What's a T1/2? It's a half-life. A half-life is a time it takes for the reaction to reach 50%. Doesn't say anything about the order or the kinetics or anything, just it takes 4 years for that thing to go half. So you can buy a bottle of this stuff and keep it around at room temperature. It's pretty stable. Doesn't lose CO very quickly. But light, it goes fast. Keep your iron pentacarbonyl in the dark. Cp cobalt CO twice. How many electrons? 5 and 9. Cobalt, rhodium, iridium is 9. So 5 and 9, we're at 14. 4 electrons here. This is 18 electron. Cobalt. Cobalt 8. Cobalt 1. D8. 1 X type. Right, this is L2X. Let's shine some light on this bugger. Pop CO off again. We just dropped 2 electrons, right? Now instead of 18, we're down to 16. This thing is very reactive. It can react with additional Cp cobalt bicarbonyl. You ever have hypothermia? You climb in bed with your buddy, share the same sleeping bag. What's going on here? This guy lost 2 electrons. It's looking for electrons, so it goes to its neighbor. You can do that some more too. Pick up some more electrons by making more metal-metal bonds. So when carbon dioxide ligands fall off, you get clustering.
Can I ask you a question about the carbon monoxide facility?
Yeah.
So when you say it produces carbon monoxide, are these facilities like, is it a waste product?
No.
They're just making carbon monoxide.
Yeah.
So when you produce carbon monoxide as waste, is it like less pure carbon monoxide? Like, why wouldn't you recollect your carbon monoxide?
Because it's a lot cheaper to just drill a big hole in the ground and suck methane out of it, fill a tanker, and ship it. Collecting it out of some waste process is not really that useful. Yeah. That's like, well, that's one of the big problems with removing CO2 from the atmosphere. There's almost no CO2 in the atmosphere. You're pulling out this minor component of the atmosphere. And that means you got to process all the rest of the gases. You're talking about taking the entire Earth's atmosphere and purifying it. Doesn't sound very good.
So then you also mentioned the energy, like density of chemical fuels and the necessity for like aviation. But then like commercial industrial carbon monoxide still coming from like a fossil fuel source. Where would like a sustainable like feedstock of carbon monoxide for like a synthetic?
Well, it would have to come from carbon dioxide.
So like
I mean, it's not that likely that we're just going to go zero carbon. There's going to be a limit at which, and I don't know where that happens, you know. Yeah, I don't know exactly where that happens, but you could capture CO2. Yeah, I don't know where that happens. I think if you're flying a plane across the ocean and burning diesel fuel to do it, you're releasing CO2 into the atmosphere in the process. I don't see them holding on to the carbon dioxide and transporting it to some place where it then gets rehydrogenated. And there would have to be a way to take it out. But there is discussion about taking like a natural gas fired plant and collecting the effluent and using that as a source of CO2. You know, maybe those are sort of near-term solutions. It's hard to think about a world where electricity is free. It's kind of where it's headed. What do I know? All right, so let's talk about attack by nucleophiles. So when you have a carbonyl like this, one of the resonance forms is this one with this positive charge out here. And, you know, you might imagine, hey, this carbon could be kind of electrophilic. Oxidation state. So if you have a nucleophile, charge in here. We'll attack the carbon with this electron pair and push a bond pair off the carbon. It's sort of a seal. How does this work? I mean, am I missing anything on the right formal charge wise, or like what's the oxidation state? Is there an oxidation state change here? There's no chemistry happening at the metal here. This is just the ligand. Oxidation state is unaffected. Where did this come from? What's that?
Still on the metal.
From the what?
Still on the metal.
It is. We tend not to write it. It's a little bit here. It comes from this. Right? You take a neutral thing and a negatively charged thing, you better get a negatively charged thing. The negative charge came from here. A little bit confusing, but you're just doing counter-strand ligand here. Oxidation state does not change. Another thing you can do is have attack by electrophiles. It's trialkyl aluminum. Is trialkyl aluminum electrophile or a nucleophile? Both, actually. Alkyl aluminums are ferocious, dangerous compounds. First in the flames in air. I'll never forget this guy. This visiting professor when I was a graduate student. He came to our group and he was using trimethyl aluminum in a glove box and basically used the vial of it. And but he wanted to bring it out. You know, it was mostly gone, but not totally gone. So he pumps the thing out and he had brought a bucket of water into the lab where the glove box was, and he pulled this vial out. He threw it in the bucket of water and blew up and exploded. And he was covered in water. He got like doused in water. We heard this like, you know, from the room where he was standing. We walked in there and he's there like water dripping out of his beard. It's kind of a moronic thing to do. Trimethyl aluminum is a bomb. Alkyl aluminums are no joke. It's like a real great way to have a fire. But they are hypovalent. Right? That aluminum's got an empty orbital, and it's going to react with this iron center just by sticking to it. Right there. Kind of neat. Why does it go to that one?
Because there are lone pairs, more lone pairs on the opposite.
It's just this better base. This is the Lewis acid, this is the Lewis base. This is more reduced than that one, right? It's a formal positive charge on that oxygen. This guy is more basic. It goes to the more basic side. How many electrons? I'll give you a hint. It's D8 16 electron square planar. You can see that over and over again. Square planar D8 16 electrons. Octahedral D6 18 electrons. It's all over the place. Platinum, lower right-hand side. Platinum 2, you got 4 things around it. It's going to be a 16 electron D8. Okay. That's a very common oxidation state. Electrons. We got 2 for each phosphine. L-type ligands, that's 4. There's an X. 1 electron. There's a plus and there's 2 electrons. So that's these 2 say cancel. 2. 6. Okay. So these compounds react with alkoxides. Do this nucleophilic addition reaction. How many electrons here? One, 2 and 2. There's 6 and 10 is 16. So it's still 16 electrons. Both are square planar. So we took this cationic thing with the CO. We added an alkoxide anion. We did some chemistry on the ligand. Nothing happened to that. Right? No oxidation state change, no valence electron count change, nothing. This is just CO count. Okay. This is one of my favorites. Rhenium hexacarbonyl cation. How many electrons does rhenium have? Below manganese. Manganese is 1 to the left of iron. That's 7 electrons for rhenium. Since it's a cation, we'll call it 6. 12, 18. E6, 18 electrons. Just like I told you, right? D6, 18 electrons, all over the place. Chromium hexacarbonyl is D6, 18 electron octahedral, just like that one. Rhenium 1. All right. So you take that molecule and you throw it in labeled water, like O18 or O16 or something. It will actually react with water and lose a proton. Still rhenium 1, still octahedral, still 18 electrons. And then it does this thing. This hydrogen moves over to the other oxygen. And then that H plus comes back. This time it loses the other oxygen. We just swapped the oxygen with the water. And these are microscopic reverse steps of each other. You can go either direction. And in fact, all of the oxygens will switch. You can fully label rhenium hexacarbonyl cation just by stirring it in water. Labeled water. So 6 CO ligands and a positive charge. That compound is electrophilic and it even reacts with a wimpy old nucleophile like water.
We basically capture the oxygen. And you're saying you exchange the oxygen, but you put the oxygen from the water onto your molecule and then you release it in water. So what can you do with that? How can you, that gives you selectivity in a reaction, right? Atomic selectivity, it doesn't give you another type of selectivity.
Well, it gives you a new substance. I mean, you might want to make labeled water, the carbon monoxide, or you might want to make a labeled transition metal complex like that for some other purpose. And that would be a slick way of doing it.
Why is that like D6?
Well, it's a rhenium cation with 6 neutral ligands around it, right? And rhenium starts with 7. That makes it D6. Right? Manganese, technetium, rhenium all start with 7, so as a cation, that makes it 6. Is it the carbon monoxide piece that's confusing, or?
I guess the way I've been thinking is probably, it's wrong, but the way I've been thinking about it is like it's got 5 d electrons to start with.
It has 7.
It's 7.
Yeah. Iron, ruthenium, osmium have 8. Cobalt, rhodium, iridium have 9. Nickel, palladium, platinum have 10. Nickel, palladium, platinum have 10. That's the end of the transition metal series. Copper, silver, gold, and zinc, cadmium, mercury, they're not really transition metals.
So are those S electrons? Are we counting those as D electrons?
You're talking about, yeah, so the 10 valence electrons are all considered to be part of the D manifold in complexes. The real occupation has some S character mixed into it. And in an atom, in the gas phase, you can get SD. So, you know, you might have S1D9 or something like that. But in a complex, we just assume all the valence electrons are in the D orbitals. Okay, so manganese, technetium, rhenium have 7, iron, ruthenium, osmium 8, cobalt, rhodium, iridium 9, all D electrons. So this is D6 because we lost 1 electron from the starting state, which was D7. Okay, so here's another good one. I think you might remember it. Lithium, tungsten hexacarbonyl. Oxidation state here. Still tungsten 0. A little wonky, right? You got this X-type ligand and a negative charge. That's a tungsten 0. If you then take this thing and you add Meerwein salt, this thought is really cool. Trimethyloxonium BF4. Pretty carcinogenic. Anything that alkylates your DNA electrophilically is going to give you cancer. It's a lovely reagent. What's that? Recognize that? Anybody? Don't recognize that? It's like my favorite molecule. What's going on with that ligand? Am I missing anything? Or what kind of ligand is that? Is that an X or an L or what is it? An X? An X type ligand or no type ligand? Why is this hard to answer? Why am I, what's different about it? Yeah, that's true. What's so special about that? It's got that nice little resonance. All right, put your notes away. I mean, this is, is anybody bothered by this drawing?
There's no plus sign on the oxygen.
There you go.
There's no, yeah, so the oxygen.
Where's the plus sign? 3 bonds to oxygen. That's like a Texas carbon, right? Better have some plus going on out here. And this thing is neutral because we took an anionic thing and we added a cationic methyl to it. So this is neutral. So if we're going to write a positive charge here, we got to get some negative charge in here. Yeah.
I'm confused because on the reaction drawing something like trimethyl oxide.
Yes.
And we only have one methyl.
Right. So you would lose dimethyl ether. And there was some cation here, lithium, not drawn. And so you would also lose lithium BF4. Okay. There's a resonance structure we could draw for this compound. Oxidation state here is probably the same as the one behind me, because we just did chemistry on the ligand. Zero. Tungsten 0. What's the oxidation state here? It changed? It changed. We changed the resonance structure. Which is a better description? Fischer carbines are better described this way. It's somewhere in between in reality. Remember, you can dissociate this thing like this. You can pull off that neutral closed shell fragment. So that's like bringing up a neutral lone pair, just like a phosphine, right? If you pull this thing off, then you're just left with tungsten pentacarbonyl. And it looks pretty clearly tungsten 0. So these are like that. All right, here's another good one. This is some classic chemistry. Oxidation state. Could be iron 1, but sorry, this thing is a cation. Okay. Iron 2. One X type and a cation makes it iron 2. CP is kind of like 3 ligands, an X and 2 L's. You got 3 ligands down here. So this is quasi-octahedral. How many electrons on the iron if it's iron 2? It's D6. Probably 18 electrons. Octahedral D6, 18 electrons. 5, 2, 2, 2. I'll just say 6 this time. I shouldn't do that. 8 minus 1. So, 13 minus 1. All right, so this compound reacts with base. And it reacts with more base. After doing nucleophilic addition, it gets deprotonated. And then guess what it does? Anybody have a guess?
Is that a minus sign on the oxygen unless that when it's hot?
You gotta guess.
It's a loose carbon dioxide.
Organic chemist in the house. This is CO2. And it makes a very famous compound called the fifth anion. Oxidation state here. This is like the other one. One X-type ligand, anionic charge. You can dissociate CP anion from this thing. You'd be left with iron dicarbonyl. Iron 0. How did we get to iron 0? We were an iron 2 land over here. You just added base. Where did those electrons come from? Where do the electrons come from?
They come from the base.
From the what?
The base.
Kind of. I would say it slightly differently. They come from the carbon monoxide. You're making CO2 as a byproduct. Okay. We lost our lone pair on carbon. CO2 is a reducing agent. It burns in air. It's real flammable. Weird, because it's hypovalent. So it burns in air. So when you put a second oxygen on there, it brought its own electrons to the party. Okay? Carbon gives up 2 of the electrons it had, exchanged for this oxygen, and the iron collects those 2 electrons. The combination of CO and base. Okay, so we'll come back to fifth dimer or fifth anion later, I think. Let's stop at this point. All right, that was fun. see you on Monday. Send out a doodle poll request. You have sent. Some have not yet responded. Have not responded to the doodle poll request about moving the exam time. You should do so. We can't move the exam unless we have everybody agreeing that it's okay to move the exam. Right? So please respond to that request. Yes. Having that.
I don't want to do it. I think we should ask him. I also think like we can tell him what we can ask him for a day after. Like that was I just don't know what to yeah. So the one that's winning right now is Friday. And I think you're gonna be something about yeah.